My name's Arthur Doler, or Art. You can call me whatever, I don't care. I come from the far-flung lands of Nebraska, which is not so far-flung as most NDCs I've been at, with like Oslo and London. But I work for a company there called Avature. Nobody's going to see that. Great, that's fine. We do consulting. So I am a software engineer. I'm not a psychologist. I'm not a psychiatrist. I'm barely even a data scientist, I guess. I solve problems. I just happen to do it with code most of the time. So that's kind of where my mindset is and where I come from. My Twitter's up there, my Gmail's up there if you have questions afterward. So I know you're not supposed to do this in a conference talk, but I want everybody to take their phone out and just find some app that has predictive text in it, like your texting, messaging app, whatever. Something that will have a predictive keyboard. And I want everybody to enter in the nurse said, and then space, and see what the next suggested words are. How many people's results included the word she? Pretty much all of you, most of you. How many included the word he? 3, 4, okay. There was a 5th. It's a pretty clear swing there. Now try it with this one. The software engineer said. Anybody see she in this one? 2? How many see he? There we go. This might seem like it's kind of spurious and it doesn't really matter, but this is the kind of thing that lurks on the outsides of our cognitive experience. This is the kind of undercurrent in society and in culture that can actually shape behavior when we're not paying attention to it, or shape behavior of people who are growing up in that culture and society. And this becomes really important because we are starting to make a lot of use of AI and machine learning. We're using it because it's becoming easier to do. There are all kinds of tool sets out there now where you can just throw data at something and it will construct you a model that's predictive of something. And it's becoming more powerful. Stuff like TensorFlow is ridiculous. You can do deep learning and reinforcement learning and you have no idea what you're doing. And we're using it to solve complex and important problems because that's generally what we try and do. Things that are going to save people money, things that are going to actually mean something or do something in the world. And we're using it to supplement the workforce. We're using this for things like office automation. And because we're using it primarily for those two things, the complex things, or because we don't have enough people to run this, it means that we can't stay on tabs with it all the time. We can't pay attention to it. And so when it breaks, we might not even know it's going to break. Because if we were just going to monitor the output all the time, then we might as well just have a human do it. And sometimes we don't even know how it works. When you feed some data into something like TensorFlow and it spits back out a model at you, can you describe what that's actually doing? Even if you're using some more traditional data science techniques, things when you start recombinating columns or when you're using a neural network, you can't explain why something occurred. I mean, you can explain the math, but that doesn't mean anything in terms of symbols or language. And the most important thing is that because it is getting so easy and because it is becoming ubiquitous, more and more people are doing it. Regular developers like you and me are writing these things. We're creating models, we're creating predictive things, we're creating classifiers. And that has some real consequences if we're wrong. Take, for instance, risk assessment software. This is software that is used either during parole hearings or during sentencing hearings to display the risk that an offender, a criminal offender, will be recidivist, will reoffend, basically. ProPublica did an article on this. This was in the news, very large study. These are risk scores. They go from 1 to 10. And those are the counts. So it's just a standard histogram. The top part of that chart is for black defendants. The bottom part is for white defendants. This gets worse because later, most of these programs have been found to be no better than flipping a coin at actually predicting whether somebody's going to reoffend. But you've just sentenced somebody to 3 years to life, or 30 years to life. Congratulations. This can actually ruin lives. And it can happen without us even thinking about it. Imagine if you were trying to work on some kind of natural language processing algorithm, something where you're doing sentiment analysis, where you basically evaluate the words and determine whether it has a positive sentiment, whether people are happy about a thing, or whether it's a negative sentiment, they're not happy about a thing. And then you put in some sentences involving first names from people with various ethnic backgrounds, various traditional ethnic first names. I spy an outlier. How about you? I mean, if you look at the far right over there, white names have a higher sentiment value, higher mean sentiment value, and a lower error if you look at the actual whisker plot. I don't want to come at you this day, and this is not about fault. This is not about blaming people. This is not about asking who did it, who done it, and I'm going to be talking about a lot of different things today where these things have come up, but it's not I'm not blaming somebody. I'm not trying to call them out and have us all yell at them in a big circular yell fest. That's not helpful. What I'm trying to do today is talk to you about responsibility and to talk to you about the reality of this data and what it does and how we tend to behave with it. And so today, we're going to talk about 6 different classes of problems with AI and machine learning. And because I am a huge nerd, I have decided that these correlate with the classes of ghost from the Ghostbusters movies. And that kind of fits with how I like to think about them. These things are like our cognitive biases, just they're there. If we don't pay attention, these things tend to creep in. They're the ghosts in our machine learning. And while I may not have a degree in psychiatry or psychology, it's very possible I have a degree in parapsychology. And I know what we do with ghosts. We bust ghosts. So today I'm going to be giving you some tips, some ways to think about this to help you overcome some of these problems. Some of these are things that science has been doing for a while, and we just need to catch up. Some of these things are big, untractable problems that I don't have firm solutions for, just general guidelines and suggestions of places to look for solutions. This is a really hot topic. I was revising this slide deck literally this morning because new things keep coming out. The first time I gave this talk a couple months ago, there was another speaker giving a talk on the same topic, and we had one overlapping example from 2 one-hour talks. This stuff happens a lot, and it happens everywhere. So we're going to go through each of these in turn. Phantoms of false correlation, specter of biased sample data, the shade of overly simplistic maximization, the simulation surprise, the apparition of fairness, and finally the feedback devil. So we're going to go through each of those in turn and talk about what we can do. We're going to start off with phantoms of false correlation. False correlation happens when you don't know what you're actually trying to ask. You don't know the question you're going to your data to ask. Basically, you're just going to have a big pile of data, and somebody told you you need to do a machine learning with it. And you're like, great, okay. And you just start hunting. What you do is you go fishing. And if you go fishing and you don't know what you're trying to catch, you can wind up with something and think it's way better than it actually is. You can find these arbitrary correlations, and you can become confused and think that they actually predict something, which isn't necessarily true. So for those of you who don't know what correlation is, here's a really quick summary. Correlation is basically the fit between 2 data sets. So we have 2 data sets here, the red triangles and the blue circles. And I've shown the dashed lines, which is more or less the distance between these. And you can take that distance between those 2 points and subtract the distance, or subtract the 2 values, get the distance, then take the square root of it. Eventually you get the mean squared error, don't worry about it. I'm not going to go too heavily into math today. But when you just look for correlation, you can wind up at some pretty weird places. These are from the amazing site spurious correlations. Correlations happen naturally. Things correlate with each other. I mean, as much as I would like to believe that the number of people who drown by falling in a pool is related to the number of films that Nicolas Cage has starred in, pretty sure it's not true. And I'm pretty sure the divorce rate in Maine has nothing to do with the per capita consumption of margarine. And I'm definitely sure that the letters in the winning word of the script spelling bee has nothing to do with the number of people killed by venomous spiders. But, as you can see, those are pretty highly correlated. It's really easy for our pattern matching brain to look at those things and say, oh, look, this is something that's meaningful. But it's not, it's just a correlation. This is kind of the easiest, most common error that we're gonna run across. And it's the easiest that you can get rid of, the easiest to deal with. So what you can do about this is just start by knowing what you're gonna ask up front. Going to your data with an actual question, saying, well, what predicts this? I wanna see what correlates with this, and asking that question. Because if you just go looking in your data for correlations, you're going to find them. Machine learning or not, humans are very, very good at finding patterns. And we tend to have built that into our machine learning tools because patterns are useful, both for us and for them. You can also try using conditional probability over correlation. And conditional probability is a way of saying, okay, if I have the probability of probability of B, given that A has happened. I said I wasn't gonna get too deep into math, but this is the math for it. If you actually care about probabilistic math, it's a way of basically saying, okay, what is the probability that this one event is caused by this other? If A happens, what is the probability that B happens versus the probability that B happens alone? If it changes, you have the start of an actual causative explanation. So you can try and use that instead of just going and looking for correlation. Then there's class 2, which is the specter of biased sample data. This is the most common one you're going to see. Like, class 1 is so broad and it happens so often that most people aren't even going to talk about it. But in the media, things like that, this is the thing that gets a lot of play. More importantly, because it's really easy to screw up. So you might not understand what I mean by sample data. Let's clarify. So you have a big pile of data and you're working to do something. Let's say you're working on an app for mortgage lending analysis. And you have a big old pile of data that you want to do things with. Typically, machine learning algorithms can't run on, if you've been around since like the 1940s as a company, you have enough data that it will choke most machine learning algorithms unless you happen to be Google. And so we deal with that by taking that data set and breaking it off into a sample set through a process that can be complex. Once we have that smaller sample set, we usually break that into 3 different parts: the training set, the test set, and the validation set. We do that because we want to be told that our phone is making a lot of noise. Apologies for that. In the bag. We want to be sure that when we train something, we then test with it and we say, okay, did that work? Each of these successive breakouts is a way for us to avoid what's called overtraining, to avoid matching exactly to that limited training set. And our data is usually shaped something like this. In the case of the mortgage example, you have standard things. You have this, an ID column because we're in a standard ACID database. You have an age and income, and married, whether they were approved for the loan or not. The right-hand column there, dependent, is the approved column. We're calling that the dependent variable because that's the thing we're trying to predict. All the rest of these can be what's called independent variables. And they can be predictors. And a predictor is something that will predict that dependent variable. The problem starts to be that we almost certainly in our data set have things like this. Columns that are like race or gender. Data sets can be biased. Your data set can contain bias from humans. And I'll talk a little bit about why that is. But most importantly, what I want you to come away with is that the output of a system that is working on that data will also be biased. Now, it's not bad for an algorithm to be biased. That's kind of the point. You just want to make sure that it's biased in a direction that is, you know, legally and socially and ethically responsible. Because when you build things like a classifier, or you build things like a predictor, or some kind of linear regression, you are telling an algorithm, I want you to be biased in this particular way. And that's fine, because that's what they're for. We just have to be careful about garbage in, garbage out. Your data isn't just data sitting there. Data at rest is not valueless. It is not judgmentless. Your data is shaped. It was shaped not only literally in terms of what columns are in it and what data was actually recorded and the process that created it, it's affected by the system that created it. If you're tracking outcomes from, say, the mortgage industry, like we've been talking about, if you're including dates around the 1950s in your predictor, you have baked in some pretty bad bias into your system because the outputs, the things people were doing at that time, things like redlining, et cetera, show up in the data. Yes, it is just what the adjusters did, just what the bank people decided in terms of the loan, but that output, their behavior, is recorded in that data. We're literally transcribing that bias into the data itself. And it can get really, really hard to get it out. Amazon spent quite a long time working on an AI recruiting tool that they literally, they've tried recombining it and figuring it multiple times and eventually had to give up. They literally could not get it to not be biased against women. And it's not like this is some Archie Bunker, I don't remember his name on Married with Children. This is not that the algorithm itself is like beer swilling in a, undershirt and watching terrible things on the couch. The algorithm is sexist not innately. The algorithm is sexist because the data that they were feeding into it, they couldn't work to cut that bias out. It would have been too much work because the data that they were feeding into it, this information about how people talked about women in their resumes, the things on resumes, how Amazon even considered people to be effective Amazon employees, all of those individual changes, individual processes, individual cognitive thoughts get recorded as data. And then the machine looks at them and it operates on them. It's not like it's inventing things out of whole cloth. It's just looking at what's already there, baked into that data. And you can see this in a bunch of really subtle ways too. This is an amazing tweet that I got permission to use, thankfully, because she had to take it down because she was worried about the company, which I have not mentioned here, getting dogpiled on Twitter. And then if you can't see what it says is unusual word pair. It seems that the noun girl might combine better with an adjective other than successful. Consider rewriting this word pair or choosing a synonym for successful. And the suggestions it gives are lucky and happy. This stuff can get real pervasive and it gets real hard to get out. To be fair, the company in question immediately saw the problem, said oops, and worked to fix it. But unless you consider these things up front, unless you consider the data source up front, you're just going to be bug squashing. You're going to be encountering these kind of problems consistently and constantly. And when you're doing this sort of thing, it might be that your sample isn't representative. That process of building a sample data set can be complex because you want to get a representative data set, a small data set that represents everyone in that larger group. But your data itself might not be representative. If you're tracking data from things that people do online, at the moment you are tracking only about 50% of the global population. And what happens when more and more and more of those people keep coming online? Their data hasn't been tracked. They're not in your data set, and your data system, regardless of what it is, will function very poorly for them. So what can we do about this stuff? How do we grapple with the specter? Well, the first thing I want you to think about is that a model represents what was. It doesn't tell you what should be. That's your job. That's my job. That's our job. We look and we say, I would like to build a model out of this particular piece of code or out of this particular data. And the machine will do that. And the model That data represents that past history. It's a record of human action. It's our job to say, okay, does that model match what I want to happen in the world? Because you have the chance to not just blindly follow whatever Google spits out at you. You can even find better data sets. ConceptNet.io has one where they've been working very hard to extract bias out of a natural language processing data sets, NLP data sets. There are studies, papers that say if you take the traditional canonical data sets for NLP and run those through sentiment analysis, like you will start to see those things, those biases baked into it. Concept.net has been working to pull that stuff out. So you can find better data sets out there that people are working hard to unbias and to build. You yourself can build a better data set. If you're taking the mortgage example, you could just say, okay, from this point, we're going to assume that everybody is doing their best work and has their best foot forward, and everybody's doing their best job. And from this point, we're going to track that data and build a new data set from there, ignoring historical data. You can also just not feed those columns, problematic columns, into the predictors, into the machines that generate those predictors. Just don't pass in race and gender. See what happens. Maybe you can find another one. There's a problem with that, though, in that you can find these shadow columns. Let's use the mortgage example again. Race and zip code, pretty highly correlated in America. So if you have a zip code column, but you've removed your race column, oops, you've still got that bias lurking around, even though you thought you've gotten rid of it. There's really good examples of this where there was a researcher who was passing data in to, it was a genetic algorithm, or excuse me, adversarial neural network that he was passing information into, and he was trying to get it to classify images, and it learned that he was passing in alternating images, one which was supposed to pass and one which was supposed to fail. And so with the algorithm, it's like, oh, okay, the neural network just basically would alternate pass and fail. It didn't look at the image at all. If there's stuff in that data, the machine will learn to use it because it doesn't know that it's not supposed to. You can also try making sure your sample set is representative. There are a bunch of ways to do this. I could do a whole hour talk on it. Socialcops.com has a really good blog post on talking about how, like, 6 different ways you can work to build a representative data set out of a representative sample set out of your data set. Other things you can do is try identifying false positives and false negatives. False positives are, in the mortgage example, when somebody gets a loan and they shouldn't. And a false negative is when somebody gets a loan and they should. Once you've identified those, which usually takes a human to do, looking at that data and at least sampling through that data and trying to pick out these extreme false positives and false negatives, you can feed those things back into a learning system and try and avoid the bias that way. Literally teach the machine, no, don't do that. You don't want to do that. But there are some even more powerful tools out there. IBM has an AI fairness toolkit, which blew my mind. Like, you can go in and feed it the ProPublica data source for the assessment stuff, and it will spit out things like this. It says protected attribute sex, privileged group female, unprivileged group male. And what it's telling you there is that women tend to receive lower risk assessment scores than men, which makes sense, given biases in society. But it shows you how it's arriving at those calculations, the different metrics that it's doing to actually figure out if your data set is biased or not. This was like, they have a demo. This was doing like 3 clicks to get this thing. It was crazy. And then they offer you ways to fix it. You could do things like reweighting, weighting the examples in each of those sets, whether it's a group and a label. In this particular case, they were building a classifier out of things and trying to make predictions out of the classifier. But you can reweight the entries, the individual rows in that system. Or you can try doing something that they call optimized pre-processing. I've heard it also called, it's a data augmentation, is a different way of thinking about it. But you're basically probabilistically changing your data. which sounds confusing. Let me clarify. The first thing you're going to do is figure out your constraints. You're saying, I have a data set. Again, let's take the historical mortgage data set. And I know that I want the output of this data set to not have any bias in favor of gender or race or any of the other, completely illegal things to bias on. And once you've figured those out, you can actually go through and literally regenerate outputs from your system, probabilistically. Regenerate whether they were approved or not, based on what you want the output to be. Again, you're in control of the model. You're in control of the output and whether the world should, or the model should operate in the world like it is. You can also do adversarial debiasing, which is an amazingly awesome concept. Adversarial networks, sometimes they're called GANs. You'll see them in a couple different frameworks. Basically, you'll have two different neural networks living side by side, one of which is trying to do the thing you want, and one of which is trying to screw them up. And so it's doing things like, if you're trying to identify pictures of cats, right? This one's trying to learn cats. This one's trying to generate things that aren't cats that this thing will think are cats. So people in cat ears, okay, let's just start screwing with it. And you keep feeding it that data and telling it, no, that was wrong, and they both get smarter together. You can use this to debias your data. You can literally have an algorithm that will say, nope, this data set is still biased, and then have another neural network that will change it, and have those two compete against each other in rapid iteration to try and remove the bias from your data set. And they'll do this for you automatically. They also have another option. This one works in the actual prediction level. So even on the other side of the machine learning stuff, because you have your data, you've turned it into a classifier, and now you're making predictions. As the predictions exist, you're literally changing those predictions to match what you actually want to happen in the world, based on probabilistic and more complex things than I'm willing to want to get into at the moment. But point is that this is a tool that's out there that you can use to help you identify and remove bias from your data sets before you pass those things into models. There's also this thing, which is the what if tool, which is developed kind of in concert with Google. And it looks really complex, and it is. This is a phenomenally powerful tool that will allow you to do things like pick 2 points. You can kind of see the yellow and green one there, and say, well, what makes those two different? If they were sorted into two different classifiers, why? What did the algorithm think was important about those two? What is the data set that's different about those two? And so it, from the other end, allows you to inspect more complex machine learning processes and hopefully understand what's kind of going on underneath the hood and allow you to detect whether you want to do bias or can't have bias in the system or not, rather. They offer additional tools, which I'm not sure, yeah, partial dependence plots is up there. Partial dependence plots are ways for you to go and say, okay, I just want to look at these two individual metrics, these two individual columns. What effect did those have on each other? Is one dependent on the other or not? It's a lot of complex things, a lot of things you can do to solve this, but literally these things are getting better and better by the moment. We're finally starting to get our head around not just having a crappy data set, instead having a data set that's well-groomed, that we check for bias up front, and that we adjust to match what we want to exist in the world. And so the best tool you have at your disposal is a good process around the data science that you have as a company, as an individual. And the last thing is that you kind of need to know who could be affected in order to remove bias. If you're doing classifiers, if you're looking at individual classifications of things, you need to know if there are subsets of those classifications that are biased or not. If you're doing things like linear regression, if you're doing things like actual numeric predictors, you need to know what the inputs are to your data. It's hard to remove something that you can't even detect is there. So, going kind of up in the power scale, we have class 3s, the shade of overly simplistic maximization. Let's think for a minute about pricing algorithms, like for instance, Amazon. Most of you know that the stuff that's sold on Amazon now isn't priced by humans. It's usually priced by robots that are dynamically pricing things, and it's a very complex system. How many people have seen the reports of like these out-of-print books that are $10,000 because the pricing algorithms keep increasing like by cents every day? A researcher decided that was a really cool idea, and so he decided to put two pricing algorithms in a sandbox with each other and start just letting them go. They're both pricing the same object. They can see nothing but the price that the other one has set. They don't communicate with each other in any other way. Now we have to talk about economics for a second, so hold on. There is this thing called the Nash equilibrium. How many people have seen Beautiful Mind? That's that guy. He came up with the Nash equilibrium. The Nash equilibrium is a point where two companies with their various price curves will, in a duopoly, if they're the only two things in the market, they will either arrive at the Nash equilibrium, this balance point, below the collusion point, which is up there at the $6 mark. They'll find a point that kind of balances their profit and effort and other communication signals that are being sent between the two companies. You would expect two sane, rational algorithms, and you hope that they are, because if we have insane algorithms, then we're really screwed. You would expect them to arrive at that Nash equilibrium, or to alternately just completely chase each other to the bottom where there's no profit at all. Instead, well, and so what you would expect to see is that if agent 2 comes in at a lower price, agent 1 would drop its price, and eventually they would arrive at the Nash price together, because there's no point in not doing that. It's lower than that pre-competition price. It's definitely not the collusion price. This is basic economics. This is what actually happened when he forced one of the algorithms to drop its price. Agent 1, he forced that price down to the Nash price. You can see agent 2 follows, but not quite as much. And then the two algorithms work their way back upward to an average price. It's not quite that full cooperation collusive price, but it's higher than the Nash price. These two algorithms, doing nothing other than signaling to each other with price changes, have learned to collude, which is just as illegal when an algorithm does it as when humans do it. So I want you to think for a second about how the researcher told these algorithms what to do. Told them to go try and get profit. I want you to think what would happen if, instead of building a tool to analyze resumes and analyze incoming documents about engineers, Amazon had built a salary tool. And they told it, I want you to get me the best engineers at the lowest cost. And they didn't give it any other information. That algorithm would probably fill the entire Amazon office with women, because it can get them at 70% of the rate that it can get men. Oops. Machines don't understand things. They don't understand complexities. They don't understand the law. I have a friend who, a coworker actually, who built a piece of software, a genetic algorithm, because he's a giant nerd like I am, to determine what his food should be for the week. Like, he was just starting a family. He was encountering that whole, like, oh, I'm going to do food planning craze that people get. And so he built this program to literally, a constraints optimization program to solve like the cost versus, caloric intake versus the reusability, like whether a meal would have leftovers or not. And do they have Hy-Vees here in Minnesota? Okay. Hy-Vee chicken bratwurst you can get for 97 cents. His genetic algorithm fell in love with the Hy-Vee chicken bratwurst. It was it. The Hy-Vee chicken bratwurst, breakfast, lunch, and dinner the entire week. That was all the program's just like, no, it's 97 cents, it's high in protein, you get the decent fat, and it's really reheatable and it works. Fantastic. And so, obviously he didn't go with that, but he's like, so he had to build in a piece of information, build in a constraint that talked about variability and variety. Because the machine doesn't know that you want variety. It just knows what you've told it already. Humans rarely have a single goal in mind. We operate inside of systems. Social systems, our own brain systems. We operate inside of economic systems and legal systems. None of that stuff is visible to an AI. We have the law, we have coworkers, we have our bosses, we have individual personal goals that we need to achieve, and AI just are confused as hell because all of that is completely invisible to them. I'm going to play a short video here. This is from a data science genetic algorithm tool called Half-Cheetah. It's two-dimensional, and the goal is you're training this thing to be running. I could watch this all day. I just humping this little way along, right off the edge of the map. What the hell? What's happened here is you've told it, go forward. You've given it this reward metric that it's rewarded when it makes forward progress. If that's all you tell it, it's going to take any effort it can to get forward. Yay, one more. It's just trying so hard. So what can you do about this? What can you solve this particular issue? Well, first, remember, again, models only tell you what was. They're only mapping the data that's already there, the behavior that is already there and encoded in the data you're passing it. They don't tell you what should be in the world. So you just, again, take a step back and realize you're in control of the output. You don't have to immediately take the output of your predictor, the output of your classifier, and do things with it. But remember that people tend to trust these things, and that if you blithely display output without helping your user walk through it or understand what's going on, they might just trust in it and do something, I mean, kind of like the Half-Cheetah did. You can't trust these algorithms to make subtle or large multivariate judgments. They can't distinguish between those things. There are some things you can do. You can try using complex convoluted columns, where you're taking two columns and kind of combining them into each other and saying, okay, I want you to predict not just profit, but also happiness, some metric between the two, some combination between the two. That's one way you can do this. You can also try doing more complex algorithms that have an outside influence. Things like non-Darwinian genetic algorithms, which is a thing that I would love to give just an hour talk on that because it's a fascinating idea. It's like you don't have to follow the straight Darwinian stuff. You can do whatever you want. Lamarckian evolution, all kinds of crazy stuff. But you can do interesting things like, say, have an algorithm where you break it into two genders, and one of the genders is essentially the one that decides whether the two objects will mate, the two organisms will mate. And at that point, you can build in not just the fitness function, but build in something like, oh, does this other organism think this other organism is beautiful? And have a complex and subtle and potentially mutable by your genetic algorithm way of doing this. I mean, this is how we wound up at the bowerbird, essentially, in the real world. I mean, I don't think anybody ran an actual genetic algorithm and came up with a bowerbird, but you can use more complex systems like that to try and get complex judgments into the data you're working with. Class 5 is kind of closely related. This is the simulation surprise. This picture is from a study that was taken in a virtual simulation where they had a gripper, a robot with a gripper, and it was supposed to they were incentivizing it to move the box as far as it could. And they said, okay, that's great, and they did a couple examples, and then for one test trial run, they locked the gripper shut so that the robot couldn't open it. Instead of nudging the box around, which is what they expected, the robot learned to whack its arm in the simulation on the corner of the box, which forced the gripper open so it could use it. It found the boundaries of the simulation. Another example are these little, again, simulated composite robots, these things like individual organisms made up of robot cells. These things learned to manipulate time, for starters, to pause time so they can insert themselves into the floor of the simulation, at which point they would resume time. The simulation's collision detection would go, you ain't supposed to be there, and pull it up with this huge burst of energy. And they used that to harvest energy and propel themselves forward. Humans have evolved to take advantage of systems. That's what we do. When we give several million iterations to a genetic algorithm or some other machine learning tool, it's going to do the same thing. It's going to find the boundaries of the simulation that it lives in. And so you can get these problems and these results and these outputs that don't make any sense. What can you do about that? Well, for starters, just be ready. This is going to happen. If you give something enough iterations, it's going to find the boundaries of its world. You can try not to confuse the map with the territory. Don't confuse the simulation for the actual thing that you are simulating. When you have an output from that, look at it and critically judge it. Verify and check, does this jive with the real world? Test it out, do an experiment, see. If it doesn't, you've probably found some weird edge case in your simulation. There's a whole spreadsheet full of these things, including stuff like the half cheetah. And there was one that was genetic algorithms. Again, they were just testing it on distance as the reward function. And it just learned to grow really tall and then fall over. So we're getting up here, class 6, the second to the last class, the apparition of fairness. We've been talking a lot about that mortgage data set. Let's talk about Twitter for a second. Imagine that you are building a piece of machine learning to parse and do some prediction, some NLP with Twitter, with tweets. And I don't even know what you're doing. You're passing those in and helping people make predictive tweets that are going to get the most upvotes or whatever. I think I just crossed Twitter and Reddit, which it's early. But let's imagine that if you're unleashing this thing on the whole of Twitter, I want you to think about what happens when a thing encounters dialectical language, regardless of what dialect that is. It doesn't work so well. Most of the normal algorithms have been trained based on classical grammar. When you start encountering dialectical language, whether that's African American English or US Southern or whatever, these algorithms choke. And part of this is because a lot of AI and machine learning tools are designed to what's called minimize average loss. We talked about the correlation, the fit between those two data sets. The algorithm is in a lot of ways trying to shrink that distance between its output and what it sees as its goal. When you do this, you can wind up with a problem where there are users in a subset of the population, despite the fact that your algorithm is, by and large, highly accurate, for these subsets of population, it is inaccurate, extremely so. If it's inaccurate, do you think people are going to use that tool? Well, probably not. So if you built it off of a corpus of Twitter or tweets, and then you're expecting to build a learning algorithm where you take people's use of your tool and fold it back into that data set and grow and learn over time, those users are not learning or not feeding your data set that information. It's not learning about those users because they're not using your product because your product sucks for them. This leads to a thing called representation disparity. You can get these systems with that high overall accuracy, but really low accuracy for a subset of your populations. Even if you have data in that sample set. This isn't a problem like number 2, like class 2. You have that data, you're passing it in. The algorithm just can't handle it. And you're not checking for it because you don't know to look for it. So what can we do about this? Well, there's a really interesting paper from Hashimoto, Srivastava, Namkung, and Liang in 2018. This was a mind-blowing presentation for me to write because I'm used to writing stuff of talking about psychology and teamwork and citing papers from like 1898. Most of the stuff that I cite in here, I don't think I have a paper that I cite in here that's like older than 2013. This is big stuff that's happening right now. And so it's really hard because we're being expected to catch up and follow and pay attention to all of these things that are happening in the research field, and the communication is not always there. But from this paper, they talk about John Rawls' theory of distributive justice. Is anybody familiar? One couple people. John Rawls talked about distributive justice as a resource, that justice itself is a resource to be allocated across populations. They think about predictive accuracy as a resource to be allocated across populations. You might need to decrease the accuracy of a population to increase the accuracy of a underrepresented population. To this end, instead of using that minimum loss algorithm, or minimum loss metric rather, they talk about this thing called distributionally robust optimization. What's really interesting, this is one of the things that the FAIR AI tool uses. It's one of the options in that checkdown box. And if this seems twisty and pernicious and hard to deal with, well, wait till we get to the last one. Feedback devil. This is one that I grappled with a lot. I wasn't even sure to include it because I don't have good solutions. But I feel like it's super important. We already talked a little bit about if we build that product with our Twitter NLP, those people who use it, or people who aren't served by our product, aren't going to use that product. We're leaving them out. That's a feedback loop. Negative experience leads to them not using the product, which means their experience continues to get worse and worse because we're not helping our algorithm get better. I wish this was a less egregious example, but the example I found that drives this home the best is probably predictive policing. Predictive policing is a technique where you have an average city provided by City Skylines, a game that I spend way too much time on. And your algorithm says, I think that crime is going to happen here, based on a number of different factors. Who knows? These algorithms are definitely not public most of the time. And what happens when you do that? Well, your police department paid a stupid amount of money for the system, so it's going to send police there because it needs to get its money's worth out of it. And I don't want you to think for a moment about police behavior, et cetera. I just want you to think from a strictly job performance perspective. What happens when you send police to an area? They arrest people. That's their job. They find crimes and they arrest people for them. That means that recorded crime statistics in that area go up, even if it's just for minor things. Once that's happened, the algorithm turns around and says, crime just went up. We need to send more police. There's a pernicious feedback loop. And unfortunately, this can end with people leaving what is now considered to be a high crime area. Congratulations, you just blighted a neighborhood. Yay. This stuff can get really, really twisty and really hard to deal with. But I have a couple suggestions. First, try building your algorithm so that it knows whether something was suggested by the algorithm. Try literally carrying that information along. And when you record the outputs of arrests, et cetera, mark, say, oh, this was suggested by the policing algorithm. And then dampen those or cut them out entirely from your predictions. That's one option. But it gets really tough when you start having things like, say, money. When things turn into money and then from money back into other things, it's almost literally like that data has been laundered. And it becomes really difficult to know what is the actual output or effect of those things. The other option I have comes from the fact that I don't actually have a CS degree. I have a computer engineering degree. And that means I had to take a bunch of dumb classes in college that most CS people didn't have to take. But one of them that I thought was actually really fun was this class called Control Engineering. And Control Engineering talks about how to control outputs of systems, not in a feedback, well, in a feedback way, but not in a discrete way as treating each individual thing, but talking about the actual output of these things as a mathematical function. This is the PID model of control engineering. And it's called that because it's proportional, integral, derivative. This is a way to adapt feedback, to build a system that is resilient to things like sudden shocks. And we know this works because this is literally how mechanical and electrical engineers have been building, assembly lines since, decades and decades ago. My suspicion is that we are going to have to do something similar for the output of our machine learning processes. If you're building something like a neural network, that's just math. Almost all of the stuff that we do in machine learning and AI turns down to, it's just numbers at the bottom. And we can fit those numbers into a system like this. Maybe not this one exactly, but something that tunes it, something that adjusts it, that helps us address the feedback that's coming back from that system. So, okay, let's show this prehistoric bias how we do things downtown. We're just going to go through and sum up this stuff, then talk about some of the things you can do right now. Class 1, those phantoms of false correlation. Just know what question you're asking, and maybe try using conditional probability over straight correlation. For class 2s, you can recognize data is biased even at rest, make sure your sample set's created properly, build that learning system for false positives and false negatives, and try using adversarial techniques to detect bias. And you can use those automated tools to get there. For class 3s, remember that models tell you what was, not what should be. Try combining dependent columns and predicting that. Try using complex algorithms to get more flexible reinforcement. For the simulation surprise, just don't confuse that map with that territory and always reality check those outputs. For the apparition of fairness, consider that predictive accuracy is a resource to be allocated across the different populations in your data sets. And possibly seek an actual external audit for the bias, or for bias, or at the very least, have another team look at it. Somebody who doesn't have who's not missing the forest for the trees. And for class 7, try ignoring or adjusting for those algorithms results, or try looking at control engineering for potential answers. So fixing all of this sounds a little hard. It can feel overwhelming because a lot of this is now on us as developers, as the people who are told, go do this thing, and then we go, can I get some help to think about this? And they're like, no, you have to have it done by next Thursday. But unfortunately, the thing you can do right now that is the most valuable is just take the time to think about it. Think about the outputs of what you're doing. Think about the questions you're asking. Think about the populations that your tool is serving. And as you're building that, don't fall prey to the fact that just because math said it, it's true. Models tell you what was, not what's going to be. That's your job, our job. You can also hire a data scientist. These are people whose job is literally to do this sort of thing. They're going to be the ones with that specialized expertise to know the tools that are available and to be able to actually implement them. Alternately, you can train yourself up. There are a bunch of different tools or courses and things. I'm not going to go into detail on a lot of different suggestions. I will say that I have a tendency to trend toward actual universities. A lot of these things are problems that science itself has been dealing with for a long time. And the process of science has been crafted to help avoid cognitive biases and avoid a bunch of these particular types of errors. You can also try finding other people solving the same problems. The AI Now Institute is a good one. Georgetown Law Center on Privacy and Technology. The Knight Foundation has an AI ethics initiative. And Fast.ai is another place you can find some really good resources. You might note that I did not include any company-sponsored things up here. That is intentional. It's not that they don't exist. Google has one, or it did before it fell apart. I'm assuming they're going to try again. I believe Microsoft also has one. There are a number of other ones that are large and attached to the companies. I have some healthy skepticism about those, mostly because it's a question of, okay, what side are you benefiting here? But that doesn't mean that they can't do good work. You can also try abiding by ethics guidelines. There are a number of different data ethics and data, like information and machine learning ethics out there. There are a number of different codes. Most of them include things like privacy and content, transparency of use to the user, transparency of the algorithm you used, how it was trained, et cetera, and thinking about who owns that actual data, whether it's you, the user, et cetera. I just said I was trying not to promote companies, but I do want to say Accenture actually has a PDF out there that I thought was actually really good. And I'm saying that knowing, I'm not a huge fan of Accenture in a lot of ways, but this was a really well done paper. It actually, I mean, it reads like a marketing slick in some ways, but it does go into detail on, here's a 3-month plan for what your team should be doing as far as having a data ethics plan, data ethics rules, et cetera. It talks about a list of 17 individual tenets that your team should be adhering to for data management, et cetera. So I thought it was really comprehensive, and I wanted to make sure that I was including it. I will be up here if you have any questions. Thank you very much for coming to my talk and listening to me ramble about AI and brains for an hour. I hope you learned something.
You do your own animations?
Yep.
They're nice.
Thank you.